Welcome back. Hope everybody enjoyed their lunch. I'm going to turn things over to Christine Hardaway to introduce our next speaker.
It's my pleasure to introduce Ian Blumenfeld, the Chief Scientist for Mathematics at 26 Technologies. For the last 15 years, in a variety of roles, Ian has worked using his background in logic to ensure the safety and security of systems critical to the U.S. Department of Defense. Ian will speak to us today on formal verification for symmetric key agreement protocols.
Hi, everybody. Can you hear me? Can I get a thumbs up or something? Hello?
Yeah, you're good.
Okay, good. Thank you. Just wanted to make sure before I started talking and no one heard anything. So hi, I'm Ian Blumenfeld. As you just heard, I am the chief scientist for the mathematics research area at a company called 26 Technologies. We're kind of a mid-sized defense contractor, and within our mid-sized defense contractor, we have kind of a small research mathematics team. So I wanted to sort of, and I know some other folks here. I know, at your previous keynote, Adrian, I was an intern in his office 1,000 years ago. My background is very different, I think, from a lot of the folks at this meeting, which is to say, I really look at these things from a perspective of a logician and from a security standpoint, not in terms of attacks and the like, but rather sort of what can we say about these formally, what can we prove about algorithms, protocols, hardware, whatever the interesting thing is. So I can't seem to get my slides to advance. Oh, there we go. Okay, so what is formal verification anyway? So here we sort of when I'm talking about formal verification, what I'm saying is we are going to have some machine checked proof about some property. This could be any predicate you can imagine about a thing. I know that a thing is really vague, but really it could be proving things about protocols. It could be things about proving things about the algorithms themselves. You can certainly prove certain things about, for example, whether I'll give some examples, but whether some very common we will come up with some algorithm that's supposed to compute some fancy way of accelerating modular multiplication or something like that, and showing that it's actually equivalent to A times B mod P or something like that. Or you have an implementation, you have some software, you have some hardware that presumably implements some algorithm, and you want to make sure it actually does. Or maybe some other property. Maybe you could formally verify an absence of side channels in your implementation or something like that. So there are lots of tools to do this. We employ a lot of them. So here's like the zoo of tools on the right. These are the ones that I could find good logos for. So yeah, these are, but we've used all of these at some point. My time at 26, as well as my time with other contractors, and then some of the work I did for sort of larger tech companies like Apple and AWS. So yeah, so here are some examples. We have these sort of SMT SAT-based things. We have interactive theorem provers, and we have model checkers. These are all just some classes. This is not an exhaustive list by any means. Okay, so what I'd like to do is go at least a little bit into explaining how some of these things kind of work, and then we'll sort of pull this back to the topic at hand. So a lot of the work that has been initially done in formal verification, and this is particularly good at proving properties of symmetric key algorithms, are to use SAT and SMT solvers. And so the way, if you want to, for example, let's say you have an implementation of AES, just use it as an example. You want to verify that your AES implementation matches some specification matches, the FIPS standard for the algorithm. So you come up with some formal model of your algorithm, you translate your code into a formal model, and then you perform some sort of equivalence check. Basically, what you do is you take all of the outputs, you say, okay, equivalent inputs, take all the outputs, we're just going to XOR them all together, and then invert that. and then say, oh, is that a satisfiable assignment? Basically, what you're saying to yourself is it possible? You imagine these all as like Boolean functions, bit by bit Boolean functions on the outputs. Is it possible that these two values are ever different for the same input? And that's a basic SAT problem. It's saying, is there a satisfying assignment to this Boolean function? And if the answer is yes, then you found an input where your implementation and your specification disagree. And if not, and if it says unsat, then presumably, as long as you trust the SAT solver, you know. Now, one would believe, and you would probably be right in thinking, this sounds like a really, really hard thing to do, right? I mean, SAT is the canonical NP problem, right? So how is it that we can do this? And the answer is big SAT problems are hard. And like the entire circuit that you would reduce, AES or, a SHA hash function or any other block cipher, or any other hash algorithm or other function is probably quite difficult. It's probably quite big, and maybe you can't solve it. But there's this nice internal structure that exists in symmetric key algorithms that makes us particularly amenable to formal verification with SAT solvers. So sort of we can do this thing called SAT sweeping, and this is a picture from Alan Mashenko, his group with Robert Brayton and folks at Berkeley. Have a great tool called ABC, which does this nice and automatically, so you don't have to think about it too hard. But what's going to happen is, you imagine you don't want to try, if you try to solve the whole big SAT problem at once, it's very difficult. So what you do is you actually percolate random inputs into the circuits. And as you percolate the inputs, you find points like these points A and B early on in the circuit which are not actually that complicated. And we can try to resolve the satisfying assignment to say A and B are equivalent. And then we sort of move our way sort of in this divide and conquer strategy up the chain, looking for these cut points where you'll always have equivalence, and then you can just check those, and then if they are equivalent, then you just structurally hash them together. You basically unite the two circuits, the implementation circuit and the spec circuit there. And the result is that you solve a lot of very small SAT problems, all of which are very easy on the way to solving one big SAT problem. And the reason this is very doable in the world of symmetric key is because so there are very obvious cut points that exist, like round functions, like at the end of a round, those two things are a nice point where everything should agree. But also just sort of the structure of what these things are doing are typically not performing operations that are sort of in some sense mathematically, or at very least like bitwise complicated, right? There's lots of additions and XORs and rotates, and these things are very, very simple. The SAT equations for these are very, very simple. Whereas if you go up to more complicated arithmetic operations, like you would have in an asymmetric setting, you're going to find that these tools quickly get bogged down. Like performing even certainly if you ever have to do division, you're just dead in the water. The SAT problem for that is just far, far too difficult, even for something as small as, like, I think 32 bits is still way, way beyond the scope of what's possible with current SAT solvers. So this is great for symmetric key. It's nice. It's push button. You don't have to do very much. There are lots of great wrappers. Like Galwa has a tool called Cryptol, which does a lot of this for you. And you just write your spec in Cryptol, and you watch it just spin and go. And that's awesome. It's great. Okay. If you don't have the option of, I don't know how well you guys can see this. This is very small on my screen, which is pretty big. If you don't have the option of this, you can sort of drop into what's called an interactive theorem prover. I think the word theorem prover is kind of a misnomer. It's really a proof assistant or a proof checker. So the picture on the right shows the Isabelle Hall theorem prover. It's a problem I actually gave as an interview question once to have someone prove this thing. But you'll note if you look at actually no, that I'm wrong. This is not the interview question. This is actually even better than that. This is from some work that we did at 2.6, building out an AES, a formally verified AES FPGA core. So this is actually the specification, and you can sort of see There's the, if you know, this is the Galois field multiplication operation specified. And then there's a lemma here where we're proving that, in fact, the way to perform the inverse, which we do in the stupidest possible way, namely we just raise a number to the 254th power in the field, is equivalent to being the inverse. And you'll note if you look, we kind of have to go through this and like write down all of the tactics. We have many tactics get applied. We say, oh, we're going to substitute this value here. We're going to add in these other lemmas. We're going to call the simplifier. We're going to evaluate over certain values. And you can see that you end up with these partial goals, and eventually at the end, you'll see this done, which means you're done. The really nice thing about interactive techniques is, first of all, you can do anything you want. I mean, anything that's expressible in higher order logic or type theory or anything that sort of captures the full depth of mathematical reasoning, you can write proofs of. It's much more labor intensive. You need someone who really knows the discipline there. For protocol analysis, we have sort of a different set of tools at our disposal that we like to use. So verifying algorithms, verifying implementations, these, SAT, interactive theorem prover type tools are great. I don't know why this one bullet point is a different color. But for protocols, we use a different set of tools. CPSA, Tamarin, which you're going to hear a lot about. Tamarin is actually built on top of MAUD. And then basically the idea is, if we assume the algorithms are all secure, and then, which is a pretty good assumption in the case of symmetric key algorithms, we can use what's called the Dolovyao model of an adversary, which is to say an adversary who can replay, capture, disrupt, alter messages on the wire, but can't break cryptography unless you have, as part of your protocol, accidentally leaked a key. If you send a key in the clear, it's assumed that they could capture it and then use that to decrypt or sign or whatever they might want to do. So we have these tools, and we're going to get into them a little bit later on in this talk, just to sort of say, like, well, what are the advantages and disadvantages of each, and how does this apply to symmetric key? But I want to kind of talk a little bit more about things at a little higher level for a while. So yeah, so this is like what CPSA looks like. So CPSA is the cryptographic protocol shape analyzer. And here's an example that actually comes from some work I did with Alan Sherman and some other folks, and some folks at NSA, Ed Ziegler, and we worked on the formal verification of the secure remote password protocol, trying to verify security or security properties of that. And so what ends up happening is you have to encode the thing on the left in the language of the tool, and the thing it spits out is this thing on the right, which shows you what runs of the protocol might look like. So and if there's these colors all have their own meanings. We'll talk a little bit about a case later in a symmetric key agreement protocol about how you can end up interpreting these are shapes. You'll get a big bunch of shapes, and you're going to hope that the shapes kind of look quote unquote normal. And if they don't, you can try to interrogate why they are and ask it questions, try to prove other properties about this. Okay. So I'm going a little fast. Maybe I should slow down a little. I guess the question is, who cares? Why do you need, like, people write papers, they analyze these things. Why do we care about using all of these tools to formally verify stuff? Well, first of all, I think everyone should care. I think people are pretty flawed as reasoning tools. My favorite anecdote from this is that there was a talk when I was in grad school I cannot remember the speaker to save my life, but the title of the talk was Some Counter Examples of a Theorem of Grothendieck, which I thought was a hilarious title. Grothendieck being probably the best mathematician of the 20th century, but there were irreparable flaws in several of his published results. So people make mistakes a lot. But it's a lot of work to formally verify things, to verify protocols, to formally verify algorithms, implementations, protocol. This takes an enormous amount of effort compared to standard practice, which is think about it really hard. attack it, go test, write papers, like what are you buying here and who really cares? Well, the answer is the places that care are the places that have a lot at stake, right? So if you think about the large tech companies, Amazon, Apple, Meta, Intel, these places all employ large numbers of people who are interested in formal methods and formal verification for their code bases, for their hardware, for whatever they're building. And the reason for that is, if Apple ships a phone that has a broken secure enclave processor because some crypto is bad in it, that's a multi-billion-dollar mistake. So even though the level of effort to verify it is quite high, it's considered a good investment there. Everyone thinks everyone sort of there's a lot of stories about the foundation of formal methods, but a lot of people say, well, people really started paying attention during the FDiv bug in the Intel Pentium chips, because how could you possibly ship a chip that divides wrong? Like that's something that they should have caught, right? The government cares a lot. You'll see a lot of programs coming out of DARPA, which is the agency that my company mostly does work for. They have strong requirements for formal verification as part of many programs now. So, for example, the DARPA DPRI program was a program to build a hardware accelerator for fully homomorphic encryption, and they required that one important part that we are doing for DARPA is people are building these ASICs and we are verifying them. We are verifying that they actually are properly implementing the FHE algorithms, so BGV and CKKS. So yeah, the government wants this. There are varieties of programs that if you're interested in working with the government, you're going to have to do. And the reason is because the use cases here are pretty, like if they mess up, people die, right? So they care. They really do care. If there is a critical weakness in an ICBM system and you get an accidental launch, that would be quite bad, right? So we care a lot. Okay. So one thing I want to point out, and now let's take it back to the topic of the workshop a little bit, is why do I, as someone who does formal verification, really like symmetric key as opposed to dealing with the alternatives? So it's so much easier. The amount of work I can get done in verification when I'm dealing with symmetric key algorithms and protocols in the same amount of time is just dwarfs what I can do in dealing with things like even things just like Diffie-Hellman, but certainly if you think about the post-quantum schemes like Kyber and dilithium and all of those classic Michaelis, even if we think they're good, it's just so much harder. So here's an example. My company, as an IRAD, I wanted to build up some formally verified high assurance products. And I said, well, why don't we build an FPGA core? We'll just take the thing and build it like an AES 256 GCM FPGA core. And we're going to build it correct by construction using all of our formal methods tools. We're going to make sure we do all of this proofs. There's a whole story that goes here with a particular domain-specific language we use called a rewire that helps us take algorithms and turn them into hardware in a nice, easy way, in a way that we can then formally verify was correct. It took about 80 person hours to go from absolutely nothing to the full formal verification of GCM. So, that's not a lot of time. That's really not that many hours if you think about it. That's literally is one person working full time for 2 weeks to go from nothing to a formally verified FPGA core. In contrast, DARPA has spent tens of millions of dollars on that DPRI program trying to verify an FHE core. Lattice operations are just much harder. Anything that involves public keys or large bit widths or operations where you have to do things like perform Barrett or Montgomery multiplication, and these things just are difficult, especially if you have to make them efficient. So yeah, tens of millions of dollars. I think we're on year 4 of the program now. We're still verifying iterations of the arithmetic logic unit. It's just 1,000 times harder to deal with. So I just feel like we can get so much more assurance for our dollar if we are working in the world of symmetric key at the algorithm level and also at the protocol level. So the protocol level, let's discuss why I like symmetric key for protocols. The more the so the general rule of thumb is the more complicated the primitives in the protocol, the more difficult formal verification is. So if things are very easy and you just if things are so the tools like CPSA and Tamarin are really built, they have the notion of signing and verifying and a public key and a secret key for encryption or a key agreement or something like that. They do have some model of this, but it is much more complicated than if there's just a secret key. The analysis is takes much longer. And all this, and also if you have to, as you try to do more stuff, you end up being unable to model. So this was a problem that we ran into on the SRP verification. So as part of the secure remote password protocol, at some point you have to compute some value v plus a g to the b. So you have a multiplication operation and an addition operation. And I don't know how many of you are logicians or have ever taken a course in logic, but this is what I did in grad school. So thank you to Gödel's incompleteness theorem. If you embed you can embed a copy. Once you have a ring and can embed a copy of the integers, you can Gödel number things, and your theory is undecidable. And all of these tools are based on have decision procedures. They all have to be done in decidable fragments of whatever logic you're working in, or they die. So you have to do weird tricks. You're not even sure that you're doing it right. You're not really using the tool in the way it was meant to be used, and you end up sort of faking it. You basically make this value like a symmetric key encryption. You have to do all sorts of strange things. You have to model it as an extra layer of encryption, which it's really not. It doesn't tell you good, important information about attackers who might be able to do something to this. So they're just the analysis of protocols that heavily make use of strange asymmetric operations is more difficult, and you probably are going to actually end up proving something about an abstraction of your actual protocol rather than the protocol itself, which may be bad. Okay, so let's talk a little bit for a second about these protocols, and then I'm going to get into a little bit of a specific case. So there are two tools that I think are sort of at the forefront of this. I put CPSA. You can read that down the first column there, the Cryptographic Protocol Shapes Analyzer, and it also doesn't have a good logo, so I just put the MITRE logo. It's where it was developed. These are two different tools for analyzing cryptographic protocols. So both of them use this Dolev-Yao model adversary. Which is that adversary I said before. It's an adversary who is capable of doing things like, they can intercept messages, they can replay messages, they can block, they can do all sorts. They can do all sorts of these sort of things. They can alter messages in sort of they can send messages arbitrarily. If the channel's unauthenticated, then you'll never know. But we assume that they are incapable of breaking any actual encryption. So that's sort of the model that they use. The underlying technology that gets used in CPSA is something called strand spaces. Tamarin has a multi-set rewriting based backend. So this is the big difference in terms of effectiveness. CPSA is kind of a exploratory tool. You can still use it in the way you use Tamarin, but really it's meant to be, you're really meant to say, here is a specification of my protocol, go forth and explore and find me anything that looks weird. And it will exhaustively do this. It will exhaust all possible routes in the protocol, up to some equivalence classes, and hand you back a whole bunch of shapes and let you decide whether or not these things are reasonable runs of the protocol. Whereas in Tamarin, you have to ask it very specific questions. You have to ask it something like, is it possible that an adversary knows my, knows key A after protocol run, after a run of the protocol where, A started with this person or something like that. So you have to ask it very specific questions. It's very good at tracking them down. Tamarin is a much nicer to work with tool. I'm going to say I'm going to get a little bit of flack maybe from my own people who like CPSA. Tamarin is, I think, to sort of the general formal verification community, I think Tamarin is generally preferred from a usability standpoint. CPSA is quite clunky to get using. But as I said, there's some important people who work in NSA who like it, so we use it anyway because they believe those proofs. But also that Paul Rowe, who is one of my associate directors at 2.6, is one of the lead authors of the tool. So we like CPSA a lot. Tamarin is also great. I'm happy as long as there are formal methods people who really love their tool and will advocate for it. I'm just going to advocate for using formal verification in any capacity you want. Whatever you like to do is great. It's better than not doing it, which is what generally happens. Okay, so let's talk about where this where this goes, and an example of what I think is a pretty good success story. I'm not going to go into extraordinary depth about this. I probably could go into more, but this is work that presumably will be published. So Sophie Stevens at Arcit and two folks at 2.6, Paul Rowe and Emily Gray, who are on my team, wanted to verify the security from a protocol view of this extension to the IKE v2 internet key exchange protocol, which is RFC 8784, which includes using pre-positioned keys in a symmetric key agreement type scheme. The assumptions that are made is that the adversary, we actually endow this there's a way to endow the Dolovyau adversary with the ability to break any discrete log operations that happen. So we basically say this is a protocol that replaces the IKE v2 by mixing in a pre-positioned key into some of the key exchanges. But there still are quite a few initial steps that involve using asymmetric operations, so using Diffie-Hellman, standard Diffie-Hellman key exchanges. So the initial, so we can say that during the initial exchange in this protocol, there are the PBK isn't involved immediately. So therefore we assume everything is that we can see initially going back and forth can be known to the quantum adversary. And because of that, the adversary can launch a denial of service attack pretty simply. So so part of their analysis, I think that sort of the bulk of their analysis is understanding that you need to rekey immediately. And this is a fact that is recommended in the RFC documentation, but it's not required. So that sort of is a vague summary of some of their work. Now I want to get into, and that was actually done, I think Sophie did that with her in Tamarin and actually understood all this before Paul and Emily got involved. And Paul and Emily worked with her with CPSA, and then we found something really weird happened. So this is the weird thing. I know it may not look that weird, but trust me, it's weird. So as I said, in Tamarin, you have to ask questions, and you have to say like, oh, is this secure against X? Is this secure against Y? In CPSA, you can say, go forth and tell me all of the things. And so they coded up the protocol in CPSA, and they said, go forth and tell me all of the things. And it returned to them this thing. Now, this thing is weird. Why is this thing weird? Well, there are these dotted lines, and dotted lines are weird. So obviously, if you're not someone who reads CPSA diagrams all the time, you would have no idea that this is weird. But the dotted lines indicate that a key some value is being sent or received that is not the actual value you expect to in the specification of the protocol. That somehow something is going wrong, and the value that they're getting, the two participants are getting and receiving are not quite right. Okay, so this is not a thing that we expected to happen. You'll note at the end, though, there's a solid line kind of at the end toward the bottom of the shape. So this will explain what's happening. So this is what's called a key integrity attack. So what does key integrity mean? Okay, so I'm gonna sort of, maybe I'll go through this a little bit. So we know if an adversary can force you to use a key that's not the one that you think you should be using, that is a key integrity attack. Doesn't mean the adversary is able to do anything with that key. Doesn't mean the adversary is necessarily able to choose exactly what the key is, but they are able to make it so that you are not using the key that this protocol says you should be using. So in this protocol, remember, the beginning is just a bunch of Diffie-Hellman exchanges, and we assume that the adversary is a quantum adversary. So if Alice sends Bob this value g to the I as part of a Diffie-Hellman key exchange, and Eve can intercept it. Eve is a Dolovyau adversary. Eve is capable of replacing, altering the message, and chooses an A and replaces it with g to the A. Okay, fine. So Bob now receives g to the A. Bob doesn't know anything has gone on. There's no authentication required yet. So Bob responds with g to the R, and Eve takes g to the R and replaces it by this value g to the AR I to the -1. Okay, so by the way, the reason I have j equals I to the -1 is because I could not figure out how to get nested nested superscripts in Google Slides. I have reached the limit of my intelligence, and it stops there. So Eve replaces this by this value GAR I inverse. And so of course, when Bob multiplies that by I, Bob gets g to the AR. And when Eve multiplies that by her, when Alice multiplies it by I, she gets g to the AR, and then Bob would multiply that, multiplies the g to the A, which he got from Eve, with R, and gets g to the AR. And so they agree on the wrong value, g to the AR, when they should have been agreeing on the value g to the AI. Okay, now they still have a key that they have agreed on. Later, this key gets mixed in with the PPK, and so Eve can't do anything, presumably, because the mixing in with the PPK obviates any sort of attack, easy attack on this. But it's not right? You see in this thing, these dotted lines are telling you, yeah, Eve is intercepting and sending something, and then when we get to this final agreement, we agree, but we're not agreeing on the right thing. Okay, so I guess the real question here is, does this attack matter? Is this a thing that we actually should be concerned about? Maybe. I think the answer to this is, in general, it would be impossible to always prove, if you're going to perform a formal verification of something, there are properties that you're interested in proving things about. And sometimes, and most of the time, you might even see something like this and say, oh, this is nonsense. We don't care about this. The difficulty is, there's something going on here, right? So in the initial run of the protocol, this value g to the A we should have gotten, right? The value we should have gotten should have been g to the AI. It's g to the AR. I don't know why I chose these ridiculous letters. G to the AR, which should have been sent, had entropy that was provided both by Alice and by Bob. And Eve has replaced all of Bob's entropy with her own. So in the case that we're dealing with here, the entropy source doesn't come from the secret keys chosen by Alice and Bob. It only comes from Alice and Eve. And even if that gets mixed in, maybe that's weaker. A Dolovyau model adversary, we can't judge how many bits of security something is. That's not part of a protocol analysis. It's a weakness of sort of the Dolovyau style reasoning that we try to do here. We have no idea. There are things like related key attacks, where maybe we can sort of force ourselves into some sort of related key scenario where you could just read the message through some weakness in the symmetric key algorithm that gets used later because Eve has managed to put her own entropy in there somehow. It's unclear. The answer might be that it depends on the deployment scenario, right? Maybe we don't care about this in usual places where we would use Ike v2. But what's important is that you need to be conscious of this. So yeah, I mean, let me show you. I'll stay here for 1 second. A good example that I think from the SRP protocol, another one that I had was we found a vulnerability in that protocol where if you have a malicious client interacting with a server, you could get the sorry, I was wrong. If you had a malicious server acting with a client, you could elevate the server's privileges to that of the client. And most people are like, well, that's dumb. The server always has more privileges than the client. Who cares? That's not always true, though. There are scenarios like ones in the DoD where this does matter quite a lot. For example, let's say you are someone who's a user of a system that stores multiple levels of classification, but your client is only authorized to unclassified data. If you can access it and elevate, and this, if you can access this, if the server may only. I said this all backwards. I'm so sorry. Let's say you are someone who has a client that's able to access unclassified through top secret information, but your server is only allowed to store unclassified data. If the server is malicious and can perform this attack, they can elevate their own permissions to look at classified data. That's something that would be bad, weird, and not important in most scenarios, but bad. So attacks like this are strange and can happen. So it's important to understand what the scenario for your deployment is. So yeah, I guess this is kind of toward the end. I think I spoke faster. I'm sorry. I'm used to being in person where people slow me down when I pull my New Yorker thing of talking really fast. But what I'd say is you should verify stuff. I guess that's kind of the general feeling, which is there's a lot of really important benefit to be gained by these things. You need to understand what the attacks that are relevant to your deployment are, whether or not the attacks exist. Maybe you get lucky and these tools don't find anything, or you ask all the questions you could possibly ask and everything is rock solid, and that's great. But more often than not, you'll see some sort of strange scenario, and you have to evaluate whether or not it's acceptable or not. I think that if folks here are really interested, and I think most of you are, in making sure symmetric key based protocols are sort of the future of communication, if we don't trust either the security of the algorithms that underlie, Kyber or Frodo or classic Mikulicz or any of these other post-quantum algorithms, we're a little nervous about their security from a cryptographic standpoint. And I will tell you candidly that I am nervous about those things. I'm not a cryptanalyst, so I don't actually have a lot of evidence for this, but I just sort of I am a mathematician, and there is quite a lot of structure there, and it leaves a little bit of a taste in my mouth. But I would say that you'll get more acceptance if everything that you do goes through a formal verification process. And if your goal is to have stuff deployed, and I'm a very applied guy, I work for the government. I want stuff to make it out into the world and be used by people. It's important to do this verification. And if you don't want to do it, you can hire my team. We're always looking for work. So and if you're interested in doing it, you can join my team. So yeah, and yeah, so I have this quote from Tony Hoare. It says, the job of formal methods is to elucidate the assumptions upon which formal correctness depends, which is to say, you probably understand at the end of the day, like you may have a secure protocol, you may have a secure algorithm under the right scenarios, under the right circumstances, and the formal methods tools will keep you honest. They'll make sure that you have all the hypotheses that you need in order to prove the result that you want. And so that's about all I have. But I'm very happy to take questions, and I have my contact information if you don't want to ask me here, but I'm happy to talk here. But if you want to email me, you can look at this. Maybe you can read it from where you are. I don't know how big the screen is.
All right, we have a few minutes for any questions.
So you've got a clear message that formal verification makes sense. But it seems to be clear that it's very difficult and potentially.
I can't hear a word you're saying. I'm so sorry. I hear that you are speaking, but I can't hear what you are saying.
I don't think the room mic is working very well.
Oh, yeah, that's it was working great before.
Okay, we're switching mics.
Oh, that works. That whatever one you just used worked great.
Okay, you hear me now?
Yes, that's a lot better.
Yeah, I'm certainly very keen on the idea of the formal verification. But now, as any company, how do you make a trade-off between where do we start in the sense of how much effort do we expect this is going to be, how much expense and so on. So how do you scope this? How big is the job, basically?
So I mean, this is a good question, and this is always, I mean, so there's the question, of course, is it depends on what you're trying to formally verify, right? You know, if someone a large chunk of my recently a large chunk of my formal verification work has been on hardware, and if someone hands me something the size of like an x86 processor, it's going to take me forever. Probably it's probably not doable. But if you hand me some sort of very critical part, and that's sort of where the things lie, is if you scale your problem appropriately to the parts of it where the security flaws might exist, you know, you can sort of estimate a lot better. So, you know, as I said, with symmetric key, you know, verifications, these things are pretty fast. You know, you can get through a protocol verification. I think, you know, total number of hours spent on this was not that large. It was, you know, a couple of months at most. And then some of the work, you know, but you know, as opposed, so it's just a matter of understanding what your use case is. The other thing is, of course, it depends on who's doing it, right? You know, if I write I write Isabelle proofs, like I do that all the time, like that's part of my just sort of what I do. If you had to learn to do it from scratch, you'd have a larger, you know, ramp up time. And there's a lot of folks who are sort of interested in formal methods, but it seems like there are large barriers to entry. And actually, right now, DARPA is addressing this problem on a program called Provers that we're a performer on, which is trying to sort of move formal methods into the realm, the usability realm of the masses. And I think that their target primarily is working with like pure software developers, like people who, you know, they just write code. They just, you know, they're just, you know, undergrads who got got a CS degree. They got a job as a software developer working for some big defense contractor like Leidos or Lockheed Martin or something like that. And they're just sitting there writing code all day. Can we make things usable to them? And the answer to that is actually there are, you know, if you know, there are levels of assurance that you can get. And if you are willing to just like look at like the most fundamental level of assurance, you can get a lot pretty cheaply. But if you want the highest level of assurance, then you have to start employing people who are used to this. My experience with my team, there aren't like formal methods people out in the world who like Byron Cook hasn't grabbed and like pulled into Amazon. So my team's philosophy in general has been, if you hire very smart mathematicians, they can learn this stuff pretty fast. You know, I give people, you know, 3 to 4 weeks of ramp up, and all of a sudden, you know, they're churning out proofs in Isabelle, or they're creating models with Cryptol and SAW that let them use SAT solvers. The ramp up is not hard for people who are really, you know, skilled at you know, thinking in terms of, you know, formal mathematics. So in that sense, the ramp up is not huge. But yeah, I mean, if the problems are very hard, if it's a very complicated thing you're trying to prove, or if your protocol is very, very, you know, very, very odd or makes use of strange primitives, yeah, it's not something that's as obvious how that works.
Thank you.
Hi, I was wondering if you could comment on the extent to which software and tools could improve. And, I'll give you a specific example. So, I've been using cryptverif recently, and one of the things that I found out that it cannot do is it cannot implement a counter, like a simple integer counter that increments. And I didn't think that something like this was, very exotic or complicated, but it just turns out that it's not one of the things that's supported. And sort of wondering, what are your thoughts on, the directions in which the software could improve to handle these kinds of what I think are common use cases?
Yeah, we find this a lot. We find that, a lot of the tools in cryptoverif, I'm not sure exactly how that's being supported right now. A lot of tools, especially tools that were developed as part of academia, we sort of said like, well, a lot of tools that were developed in academia were developed so that someone could get a PhD, and then it doesn't do anything more than they needed to get their PhD. And so there are, what I'd say is, as far as additions to these tools, there are parts of the industry that are really deeply engaged in informal verification. So, for example, I don't know what your use case was, what you were using cryptoverif to try to do, but there are other tools that are under much more active development. 2.6 develops a symbolic execution tool called the Draconic Runes that we're constantly working on. Galois, another company based out of Portland, has a domain-specific language called Cryptol and a suite of tools like which is called SKAW, which works with it to do a lot of verification work. And then there's a huge community constantly working on these interactive theorem provers like Lean, and Lean has a huge user group right now. Isabel is a huge group. So the answer is, like, if you're looking for specific tools to be advanced, I mean, I think it depends on who's building them. We on provers are working quite a lot with tools that can't do things that like we would love them to be able to do. One of the big things that we've been doing has been translating some of the CNSA specifications from trying to create high assurance, formally verified implementations of the CNSA algorithms. We do this, development is all in Rust, and we're trying to use some of the Rust verification tools, and they're really lacking. They're really not built to do anything complicated. If you want to even implement, like, the finding, loop invariants are very difficult to specify, and things that you need to do in order to implement these things. I mean, I think we can do a counter. I think that's not a problem with the tools that are available, like Varus and the Cryptol version of SAW, and there's Cryptol SAW for Rust and Connie. But yeah, they're really lacking. They need people to push on them. And what we found is we just call up the developers and say, like, hey guys, we want to use your tool. It would be great. But a lot of these things are open source projects and people have limited time. But the best thing I found is get someone in the government to get really excited about it and interested in paying for it. It's really the answer, because they have money, and they'll do it.
All right, great answer, thanks.
Any more questions? So Ian, let me ask one more thing, which I might know the answer already to. It's probably it depends answer, but as we are here in the sort of thinking about getting ready for migrating to post-quantum solutions, and I know we've got FIPS 140-3 coming down the line in a year or two, and I believe there's some requirements there for formal verification.
Sort of.
On the other side, we also have I think folks in the White House saying, hey, just use these memory safe languages, it'll be okay. And I think to like some of the previous questions here, how do we figure out where we are on that sort of spectrum of what we need to do to sort of have assurance? And I know right, in some cases no the highest level of assurance is possible, yes, that's the right answer. And if we're, flying airplanes and missiles and things, right? And then there's this sort of lower end. And then there's sort of all this stuff in the middle. And I think that's often where I find it difficult to try to figure out, where, I don't know what is needed, but I don't know if you have any sort of comments or thoughts on how to better maybe match those use cases with the sort of level of assurance, or maybe there's some experience there.
Yeah, I think there's two things. So you say like, oh, people are like, oh, there's this executive order saying we need to use memory safe languages. Memory safe languages, like Rust, is awesome. I love it. It's great. It also doesn't solve all your problems. You can still, it's not like Rust doesn't have bugs, and it's also not like it's simple to like. It's not like people are not going to write a bunch of unsafe Rust that has a bunch of similar. I mean, not as bad problems maybe as C, but it's not great. So that's one thing. It also doesn't stop you from logic flaws. Formal verification is designed at its core to understand the logic flaws in your code. It's not just like, did you overwrite a buffer? Did you not sanitize your input? There's so many other things that can go wrong at the deeper logical level that's using memory safe languages is just not going to help you with. That said, you should use memory safe languages because there are a lot of bugs that are really, really bad that you end up with by writing unsafe C code. Now, as far as like where the line is, I think that more stuff really does need to be looked at formally. I think our medical systems, our industrial control systems, things that govern things like our power and internet delivery that we, somehow like are in the hands of private companies. These are what, like, we see all these people able to do ridiculous things remotely to dump chemicals and to take control of water plants that could poison huge chunks of the population. I think in the world we live in, a lot of stuff needs a pretty high level of assurance. And so it's on my community, it's on me and my people to build you tools to make it so that that stuff is usable at the level that people are going to be able to actually use it. Because, the Department of Defense can go out and pay, can run the DPRI program and pay, tens of millions of dollars to develop an ASIC to do FHE, but convincing, your municipal water supply to make sure all their your municipal water company to make sure all their code is formally verified is really hard unless formal verification is something that can be done easily and cheaply. So I think the answer is more stuff needs to be verified, and we need to make the tools better so that is actually a feasible thing to ask of people. Does that answer your question?
Helps. Thank you.
Okay.
Any more questions? Adrian?
Hey Ian, it's been a minute.
Yeah.
So the sense I get is that formal verification is still kind of an art more than a science. Maybe I'm misunderstanding, but what are the chances that we, I don't know, could get to a point where we can at least recommend strategies for getting certain levels of assurance? This spot you need to check really hard, maybe your cryptographic algorithm.
Yeah, so I think when you say it's an art, not a science, I think certainly the part where you decide how much assurance you need at any given point is a little bit like that, right? You say, oh, I want this to be fully formally verified. Well, what does that mean? What are the properties you want to check? I think that there's one strategy, one approach to this problem is probably something along the lines of there are systems in place. So for algorithm implementations, for example, you could say, let's publish our specifications in a formal language instead of publishing specifications in English. If you could specify things in some recognized formal way, then we could formally verify it. And that takes a lot of the art out of it. Sorry, my throat is super dry. 1 second. Yeah, I mean, I think a lot of the art that happens is translation from the English language paper spec into some formal model, which happens by hand almost always. If we could systematize that, if we could say that the true specification of of AES is actually this document. Maybe it's a cryptol specification. Maybe it's a, maybe it's in, some other, some SMT lib specification. Like this is what AES is. It's this thing. Then verification becomes a lot simpler, a lot easier, a lot less prone to hand waviness and guessing. We're trying to do that to standardize things. I don't know if you remember Aubin Whitley, who now works at Apple. She has started to try to standardize all of the major, NIST-approved crypto algorithms in Isabelle and have published that as part of the archive of formal proofs. So we have it is published. This is, she has it for, I think, elliptic curves and SHA and the SHA-2 and RSA and a few other things. Like this is what the algorithm is. This is the thing that your implementation has to match. That would go a long way, having these formal specifications out there. But I think in general, moving this to something that's more practical and usable is just going to involve having more people get familiar with what we're doing and building better tools to make it more transparent so that it's not like, I don't know if you ever tried to use like EasyCrypt or these tools, like they're just, that you pretty much have to like be on the phone with the developer, and like that's a problem. Sorry, did I answer your question or did I just ramble for like 5 minutes?
No, I think I see where you're going with that.
Yeah. But I think in general, to sort of systematize this, I think it's important to sort of build it in from the beginning as the way we think about things. Formal methods post hoc is really difficult. Like if you design a thing and then you try to verify it, it's a lot more difficult than if you design it in cahoots with the verifiers. I mean, that's what we used to do. When I was at Apple, that was what we did. We worked very closely with the architects so that we knew as they were building up the SCP, we were verifying it along the way and going back and forth and saying like, hey, if you design it this way, it's going to be harder to verify. Let's mix that. Let's keep these two pieces together. So that's the other thing that really, really helps make things go smoothly, is have the proof engineers and the software engineers or the algorithm designers have all of these people like in the room talking together all the time. Like more communication makes better protocols, makes better algorithms, makes better software, makes better hardware.
Yeah, that makes a lot of sense. Thanks, Ian.
Okay.
Okay, we got one last question.
You were talking about actually specifying it in producing a specification in a formal language. So using a specification language that's amenable to direct use. What about the other end of the problem? The languages we use are not designed with verification in mind. Isn't it possible to just tackle it from that side where we design languages that actually are correct in a sense from the start, like Rust has improved some aspects?
Yeah, so I think I hear what you're saying. I'm having a little trouble hearing, but I think what you're saying is that the languages themselves don't lend themselves to being, to doing formal specifications, right? I think that's true. I think we could build better languages. In fact, I was talking to a friend of mine who's in this verification space. He said, "So Ian, you're kind of on our team. You think that a good solution to every problem is to write a new programming language?" I'm like, well, sometimes. No, but I think you're right. I think that is really difficult to do well. That like building out specification languages is really hard. It's probably its own DARPA problem, is understanding how to create formal specifications that have a semantics that you can reason about in something like a theorem prover, or you can discharge to an SMT solver, but also is expressive enough to be able to say the concepts that you want without it being weird and clunky. We've had this issue, like Cryptol is a great language for specifying symmetric key algorithms. It's actually quite nice. It's very easy to read. It looks exactly like your spec. It looks like what you would write on paper. Then you move it to anything other than a symmetric key encryption algorithm or a hash function kind of, and it kind of loses the thread. It really is not designed. It doesn't work well for that. How do we do this? How do we write these languages? This is a good research question, honestly. I think this is an important problem. And I think that people keep trying and getting it a little bit closer, like we're asymptotically approaching, or maybe not asymptotically, maybe we're not actually approaching it that fast, but we're approaching, we're definitely making improvements. And I hope that we're getting asymptotically close to the right answer, but we still got a ways to go before I think we hit the threshold where we're comfortable with the languages for specifying these things. It's certainly true that like CPSA, it's a great tool. It's a really cool way to look at things. It's really helpful. It is a nightmare to try to implement anything more complicated than what the basic protocols it was intended to look at, like Nina Schroeder, in it. It's just not super easy to do. You have to have, like, thankfully I have the developer of the tool like sits 2 desks down from me, so it's fine. But like, you don't have that. I mean, maybe you don't, unless you secretly work for 2.6 and attended this conference without telling me. So yeah, I mean, yeah, I think it's a good problem. I think it's an important problem, and I don't have a great answer to you other than we got to build better languages.
Okay, so it's still a ways to go. I understand that.
Yeah, I mean, I think for symmetric key, we've got some really good options, and I think if you want to, but yeah, I mean, even I went and tried to say like, oh, let me look at how you would implement these things in Isabelle. And Isabelle it's a higher order logic theorem prover. You can do anything that you can do in mathematics. You can write in mathematics. You can write in Isabelle. And it's still incredibly painful to do some of the things that you really want to do in cryptographic algorithms or cryptographic protocols. For protocols, it's actually pretty cool. Larry Paulson has this thing called the inductive method that he uses to verify protocols. It's actually quite nice. I actually like it a lot. But for algorithms, it can be there's this huge overhead to doing things that you think would be very, very simple to do, like resizing bit vectors. Like these are like it's hard. Like, and it's silly that it's hard, but it's hard. That's a function of how higher order logic works and how the type system of the tool have the type, you can if it had dependent types, that would be a little easier, but then you have to deal with how the dependent types deal with arithmetic at the type level, which is a whole other problem. There's all these weird complications with designing these languages right that you don't think about when you first start, and then you start getting into them, you're like, oh, that's why this is so hard. But yeah, we got a ways to go. It's an important research problem, and I think it's one worth looking at.
Thank you. Enjoyed the talk. Let's
Oh,
thank
thank you. Okay, thank you very much. I don't know how to. I'm going to stop sharing. Bye, everybody.
Okay, so next we have Connor Spangler, who is a solutions architect with 20 years of experience in network software and hardware development. Before entering the private sector, Connor spent 6 years as a computer systems engineer for the United States Air Force, leading the development and testing of over a dozen multi-million-dollar offensive and defensive cyberspace capabilities. I'm pleased to introduce Connor to present his talk on 13 ways to establish keys using symmetric methods and why you might want to.
How's it going, everyone? Thank you very much. Sorry, stand by. Perfect. So this is not a very academic brief. I'm not here to teach you any very fascinating, cool things about crypto or anything like that. This is kind of first and foremost what we refer to in a military context as an advocacy brief, right? And so basically what I'm here to advocate for is a new, more robust framework for symmetric key management in the context of combining some of the symmetric key establishment methods that are codified within existing standards such as ISO IEC 1170-2, however, are not formally identified in a way that lends itself well to combination, hybridization, equipping people who are implementing some of these systems in a way that enables them to effectively, easily, in an informed way, implement them in a more, I guess, robust and formalized context. So it might help to kind of establish the ground rule here, what we're talking about in terms of what symmetric key management actually is. So symmetric key management is a means to establish a cryptographic key using symmetric primitives between two parties who each have a pre-existing trust relationship. And that's either directly between each other or via some third-party mediating service. And of course, here, the two things to focus on are cryptographic keys. We're talking about symmetric keys for symmetric ciphers, and the fact that we're using symmetric primitives to identify those ciphers. So why do we care about symmetric keys? Fundamentally, symmetric primitives, they are more robust. They are safer against a wider spectrum of attack vectors. You can consider that things like asymmetric algorithms that are relying upon things such as large prime number factoring or solving discrete logarithms. These more complicated mathematical processes do lend themselves much more to things like sidechain attacks, for example. And as mentioned in Ian's outstanding brief, there's also the threat of cryptographically relevant quantum computers to several asymmetric algorithms such as RSA. And that, of course, is something that a block cipher like AES, for example, is considered to be immune to. Or if not immune, at least drastically reduced threat. And additionally, symmetric primitives require much smaller keys relatively than asymmetric. So, for example, in order to achieve the same relative cryptographic security as a 256-bit symmetric key, you would actually need over an order of magnitude larger key length, something on the order of 3072 bits of an asymmetric key to achieve kind of the same security benchmark. There's obviously a significant difference in terms of security. Symmetric primitives also are more diverse. So you have kind of many different ways that you can actually operationalize these. Block ciphers where you're encrypting blocks of data, chunks of data, stream ciphers where you're streaming bit by bit or byte by byte in real time. And then you can also break those down into many different modes of operations, things like Galois counter mode, GCM, which is used every time that you're using TLS, for example, today. And then finally, they're much more agile. So we have the concept of things like crypto agility, where it's very easy to swap different symmetric ciphers out in the case. For example, if a vulnerability is identified, one that you're using in your implementation, or maybe you need a different kind of set of use cases addressed by a symmetric cipher that you need to swap out. It's very easy usually to do that with symmetric, not so much with asymmetric. And that's largely because of the kind of difficulty, the complexity of implementation of things like asymmetric schemas when you're having to leverage things such as PKI, right, or public key infrastructure. And one of the other big benefits is that because symmetric ciphers are so efficient, they're low power intensive, very easy to implement, they're ideal for things like bulk or rapid encryption and decryption for things like IoT devices, edge devices, where you don't have the luxury of having large amounts of compute maybe. And so we're talking about symmetric key management and actually implementing symmetric key management at scale. There are a couple of major requirements that identify for actual implementation. First and foremost, you need to have some type of way to get the keys introduced to systems that want to consume them in their ciphers. And so we do have several different standardized ways of doing that today. We have things like the pre-shared key mechanisms that exist in TLS 1.3. We have RFC A74, which you mentioned in his own brief, he did the analysis for. We have Tamrin, which allows for pre-shared keys to be introduced for IKEV2 for things like IPsec tunnels. And then RFC 9420, which actually allows for PSK ingestion at the application layer. And at the end of the day, what we're talking about for any of these, whichever way you do it, you're basically just talking about getting the same shared random string to parties that need to leverage it for establishing these symmetric keys. And the other half of the equation for implementing symmetric key management is that you need the protocols themselves that are secure and practical based on those symmetric primitives to actually leverage the key material itself. And so things like classic Kuros, right? Kuros, which is allowing for authentication to secure services over things like untrusted networks. And when I mentioned before, the standard ISO IEC 11770-2, I'll try and say that as few times as possible because it's a mouthful. Going forward, we'll just refer to it as the standard. But it is a standard that establishes specifically 13 different ways to execute the symmetric key management process. And they're spread across a few different categories of implementation. And those categories are what we're going to be focusing on when actually discussing how we can standardize a framework that lends itself much more readily to actual real-world implementations of some of these symmetric key management methods. So as part of the standard, again, 3 different classifications. Number 1, you've got your standard point-to-point, where you have communicators that have already established some type of trust relationship. They have some shared secret material, and they want to establish further keys, right? And so in this case, when you have point-to-point, you do not need some third party, no mediating authority, no key distribution center. And this is ideal for things like your TLS session resumption tickets, right? If you've already established a session and maybe you want to resume that session, you don't have to go through the entire re-agreement process. You can use these session resumption tickets to do that in an efficient and rapid way. And part of this, you do not require that third-party assistance. However, there is the limitation that point-to-point, you don't have a luxury of being able to kind of dynamically establish keys with additional parties or any parties that are kind of outside of that trust relationship. So we just to the second classification, which is what I mentioned, the key distribution methods. This does allow kind of a third-party broker, a mediating authority to provide identical secret material to multiple parties that want to agree keys together or establish symmetric keys together. This does require a pre-existing trust relationship or a shared secret, but between the communicators and the mediating party, it does not require that the actual communicators themselves have one with each other. And this is great for things like ticketing servers, again, things like Kerberos. And one great benefit of the key distribution center methods is that it does allow for centralization kind of resources, you know, in the form of that key distribution center, of that third-party broker, which is great for, you know, large, massive distributed systems where you have thousands, tens of thousands, millions of endpoints. You don't have the luxury of being able to do single point-to-point schemes between every single permutation of those endpoints. And then finally, we have things like key distribution. And these are basically methods that allow a third-party mediator to encapsulate and transfer secret for the purpose of key establishment on behalf of the communicators themselves. And this is very similar to the key distribution center. This does require that trust relationship exists between the communicators and the key distribution center, but not necessarily between the individual communicators themselves. And this is nice because it does keep the provisioning of entropy in the hands of the communicators themselves, since they are providing their own set of keys, and basically the key translation authority is just doing that second layer of translation. And so as part of the standard, besides just defining some of these methods and these characterizations and classifications, it does go into kind of the security considerations to take into account when you're choosing which of these methods to ultimately leverage as part of your solution, right? And these are kind of myriad. You have things like key control, which party is actually has the authority and the kind of final say in the actual keys that are established. Authentication, how are you verifying that the key is authentic and it's actually coming from a trusted party. You know, replay detection is that if an adversary is able to capture and try to replay kind of key establishment messages, how is that handled? How likely is that to happen? What is your threat kind of footprint in that regard? And then, you know, key confirmation, any authentication, all these things in a nutshell are basically just getting after how do you qualify the types of qualify and categorize types of security considerations you have to take into account if you're going to leverage any one of these methods. And then beyond just the security implications, you also have to, of course, get into practicality, right? Because if you're working with a solution set where you need maybe tens of thousands plus of endpoints to be keyed to each other, then obviously the practicality of doing point-to-point methods is kind of overweighed by the practical limitations of actually establishing that, especially if you're like in a low bandwidth or low throughput kind of network environment. And all of these things, things like, you know, number of passes, how many different round-trip message exchanges does it actually take to be able to ultimately establish keys between each other, the complexity, the number of encryptions and decryptions required. All of these are considerations that actually have to be taken into account. And, you know, factored into the calculus to determine, is this not only a secure solution, but also it's practical based on my use case and what I'm trying to apply this method towards. So then we start getting kind of beyond the standard, right? And this is where we start getting into what we're advocating for here as part of the framework. Because at the end of the day, of course, all of these different, 13 methods, symmetric key management, they can all be implemented kind of in a vacuum. Sure, you can implement them one-off to address single one-off situations or use cases, but at the end of the day, in the wild, these are often, if not almost always, combined together into more complex systems to actually enable large and distributed systems to execute kind of this symmetric key management process. So, for example, you might see a situation where you have some initial provisioning of bootstrap keys to individual communicators, and then they can use that bootstrap key to establish point-to-point communications via the point-to-point methods. And then you can extend that to where those pairs of communicators or users are now using distribution or translation to produce additional keys. So maybe go outside of their geographic organizational boundaries. And then you get to a point where basically all parties in the entire equation are now contributing entropy to this larger distributed symmetric key management system. And ultimately, the design and considerations taken into account for these systems will come down to the use cases and the constraints that are imposed by the actual implementation itself. And to that end, the standard does not necessarily cover all of the security considerations that start arising out of the process of combining these approaches into a single solution. So while the standard does a very great job at drilling pretty effectively down into the individual details of security considerations, practicality considerations for individual methods of symmetric key management, once you start combining them and creating more hybrid systems, that starts becoming a much murkier target to analyze and apply to your actual use case. So Kremers and Horvat actually took it upon themselves in a paper not too long ago to actually explicitly approve on the ISO-IC, the standard for key management techniques. And they dove into kind of the different things that are not addressed by the standard, but are critical for actually effectively analyzing these potential options for real world solutions. Things like Lowe's authentication hierarchy. How do you actually qualify and define what authenticated means in terms of maybe key authentication or entity authentication? Things like key freshness. How does the rate of rotation of keys, the rate of refresh of keys affect your security baseline? And also, how does it factor into practicality? Is it even viable to rotate keys or refresh keys at any type of sustainable rate? Forward secrecy, where an adversary's ability to somehow manage to compromise a key used to encrypt some session, does that or does that not enable them to derive keys used past that point and compromise any future communication after that point? So all of these are kind of factors that they brought into the fold as part of their analysis that are a great way to expand upon the framework. However, of course, they're not formalized. They're just basically suggestions to address what they perceive as the shortcomings in the standard itself. And beyond just the security considerations that exist beyond the standard itself, we also have kind of the security philosophies that have become more ubiquitous over the past decade. The standard itself was written in about 2018, so it's been about 6 years and some change. And since then, a lot of these concepts that you see up here have become more and more kind of adopted and more robust. Things like crypto agility, again, the ability to swap out different ciphers and schemas as security dictates or as needs dictate, defense in depth, layering of multiple different security systems in order to create a much more secure system. Zero trust, of course, trust no one, encrypt everywhere. You're talking about, especially encrypting everywhere, every single subject in the system is encrypted whenever communicating with any other subject in the system. And that requires obviously a much more robust symmetric management system if that's what you're leveraging to actually achieve that. And then, as we discussed before already, quantum resistance, right? That's a security philosophy that is now becoming more mandatory, especially at the government, DoD, IC standpoint. And the kind of problem with discussing the security philosophies is that as opposed to something like security principles where you can quantify discretely the number of passes that it takes to establish a symmetric key, or the number of encryption and decryption steps it takes, these philosophies are very difficult, if not impossible, to actually quantify and say, yes, this meets the mark, or no, this does not meet the mark. Yes, this is sufficient. No, this is not sufficient. These are much more kind of conceptual ideas fundamentally. And while industry has developed kind of best practices and developed kind of a consolidated consciousness about, you know, what does defense in depth look like, what does zero trust look like, there's no checkbox or a series of checkboxes that we can apply one-to-one and say, yes, this definitely meets or no, this definitely does not. And kind of likewise, the Appendix B within the standard itself, which kind of goes into a lot of these discrete security considerations and practicality considerations, it doesn't include the full scope of measures for these methods. And in the same way that Horvath and James, wrote in their kind of treatise on expanding the standard, there's things like message size, not just the number and frequency, number of passes, but actually how big are the packets that you're having to exchange in order to achieve whatever symmetric key management system you're trying to implement. How you're actually doing like credential or key long-term management when you're talking about like storage and processing. The actual resource lifetime, if you're doing required activities, like, yeah, especially in like defense and IC applications, you have requirements for auditing and logging, refreshing and accounting and all of those fun things. Those are not addressed by the standard, but in the actual real world implementation of these methods, they are required. You can't do without them. So now we kind of bring it together and actually, we've identify, what the standard says, what it defines, how it kind of focuses on things like security and practicality. What does that really look like in the real world? And so we just have a few quick examples that I think most people will probably be familiar with. Number one, we have DNSSEC. And so if you consider DNSSEC when you're trying to get DNS records in a known authenticated way, you have things that are relevant and not relevant to the actual process of DNSSEC. So things that are not necessarily relevant, right? Things like confidentiality. You don't really care if everyone else knows what the DNS record is. You just care that it comes from an authenticated source. The DNSSEC provider does not care about request or entity authentication because it doesn't really care who it's giving the record back to. All it cares is that it's providing it. And again, Vice kind of authenticated name servers, which DNSSEC part in the back end, we're kind of talking about the requester end, not the response end. Things that are relevant, however, are things like authentic responses. You have to make sure it's correct. That's the whole purpose of DNSSEC, and making sure that the responses have integrity. And then also because DNS and DNSSEC in general are such ubiquitous and common activities on the internet, they need to have responses that are quick with a minimum number of round trips. And so between the relevant and the not relevant attributes of this, you kind of start seeing the practicality and security considerations that you're extending from the standard into the real world. And so from an actual implementation standpoint, you can consider now how we're not just talking about these symmetric key methods in a vacuum, we're actually now talking about combining them into more complex real world systems. And so if for DNSSEC can give, for example, a situation where a requester already has a pre-existing shared secret with the DNSSEC service, then at that point, we can just do something like a simple like HMAC keyed with a point-to-point scheme, which would be a totally fine solution for getting those DNSSEC records. However, if no pre-existing trust relationship exists between a requester and the service, now you have a situation where you might be able to leverage a third party like a key contribution center to basically enable that initial root of trust, and then subsequently go over to like a point-to-point method using like TLF revocation in the same way. Another potential use case here, like IoT sensors and edge devices. What's relevant? Lightweight computation. Needs to be fast, has to be lightweight, has to be quick, and those responses themselves also probably need to be quick because you're trying to get data in a timely and interval way. So things that are relevant, but you can kind of start spinning the slider on depending on maybe your power or how critical it is to the actual use case. You know, key freshness, how paranoid are you about security of these sensors and their data? Do you maybe not have a processing overhead to do that very quickly, so maybe turn that down a bit? Do you really need to do explicit key confirmation? Do you care as much, or do you think that there's another like a security target on your system's back that you need to do that? Again, these are considerations, practical considerations that you take into account if you're actually going to extend these methods into the real world. And so, and this type of example, again, similar to DNSSEC, you could do something like key distribution for the entire network of sensors, and then fall back to point after that. And so finally, kind of the more robust, I think more well-known example, things like high throughput, public-facing web service servers that witness massive amounts of traffic, have to handle gigabytes of data transmitting over networks, massive amounts of storage in the back end. These types of situations are ideal for a mix of mediated key agreement and also point-to-point ticketing. So this is pretty much exactly what we're describing in the form of TLS 1.3, which supports this natively. So TLS 1.3 was designed to actually reduce the number of round trips in for establishing session, and actually also includes provisions to be able to do 0 round trip re-establishment of sessions using session tickets in certain situations. And that's basically where like session state, in order to do session results, is coded directly into the ticket itself. And so this is something that is now ubiquitous throughout the internet, but this is a prime example of a situation where the multiple symmetric key management methods have been combined into a single architecture to be able to address a problem that is a solution is required for by everyone who uses the open internet pretty much. And if you were just to look at the standard by itself and try to implement this, obviously it was done because there is no framework for handling how I actually hybridize a system like this and combine these things. But the work that has to be done when architecting these types of systems to identify all of kind of the bespoke security and practicality considerations that evolve out of the development process, that's work that has to be repeated every time that architecting is done, that we can get after reducing by kind of codifying the standard a little bit better. And so that kind of brings us to the value proposition of the entire talk, right? So we've been talking about how the standard itself, again, treats all these different symmetric key management methods kind of in a vacuum. There's no cross-like, there's actually zero discussion whatsoever in the entire standard about any type of combination of methods. And so what we're really advocating for here is a more standardized, involved framework that brings all the different pieces of the symmetric key management methods and their characteristics kind of under one umbrella. And this is obviously on something of a spectrum, right? Because there's when you start doing 13 different ways to do symmetric key management, you start doing all the permutations of those methods, how extensive they are. You have multi-stage symmetric key management systems. You can kind of quickly run away and start having hundreds of thousands and tens of thousands of different systems that you're trying to describe for. But instead, what we're really trying to focus on here is enabling the interoperability, security, and complexity analysis of these systems in a way that is fundamentally easily consumed by the people who need it most. So the solutions architects, the network engineers, the people that are actually designing these systems, they need to be equipped to easily identify the requirements of their system, their use case, identify which of the methods that they need to combine or roll in to address the specific stages or parts of their use case, and then cross-reference the implications of combining those methods. You know, if you're using a point-to-point method, which gives you massive benefits in throughput, but you are required based on your solution to combine that with some key distribution center or key translation center, which requires some number of additional passes and brokerage and overhead. Have you invalidated the reason for designing the system the way you have already? And it's one thing to have to go through the entire process of doing that analysis yourself. It's another if you already have, as part of a codified standard, a rubric by which you can kind of compare what you've architected with best practices. And so basically what we're advocating for is that these new hybrid methods, new combinations of symmetric key management are able to demonstrate how they exist within kind of the existing taxonomy of methods within the standard as it exists. You know, what security properties do they satisfy? What security philosophies they aspire to follow? Obviously, if you have a requirement that you must migrate your system to some zero trust architecture, or you must achieve quantum resistance in your network solution, we have to be able to say that, yes, we know that our solution, our hybrid solution, meets that mark in some way, shape, or form. We can attest to that by showing what security philosophies they at least try to adhere to and how they actually do that. And then finally, of course, the most important thing for the actual implementation is the practical advantages or costs, because at the end of the day, you have to be able to implement it and pay for it. And so the nice thing about talking about, again, symmetric key management, symmetric primitives, symmetric ciphers, is that, especially in light of Ian's outstanding talk about doing the analysis for proving a lot of these things, is that these things lend themselves extremely well to tooling and automation and quantification and metrics. And so as part of kind of a new, more formalized, inclusive framework, security and practicality claims of these different hybrid methods would need to be justified, again, like I said, in a consumable way, and that justification can be done and itemized and presented using potentially these formalized automated tools that are repeatable across the entire spectrum of methods. And so if we can formalize that and lay out the requirements and the procedures and processes by which those are implemented and how the actual results are presented, and that can be done in such a way as making cross-referencing of the methods easy and consumable to the actual designer of these systems, then that would kind of take us a lot further along the path away from the standard as this exists now. And so that's pretty much it, guys. I mean, again, this is an advocacy brief first and foremost. We've obviously laid out the standard as it exists now, how it defines all the different ways that you can do the symmetric key management, the things that you have to take into consideration from a security and practicality standpoint, and how the standard does not address combining the methods themselves. And when you start considering combining the methods, you actually start going down the path of actually doing the work to start combining these methods together into single key management systems. You start coming across all the different interplays and ways that the security implications of one method may counteract or nullify the security implications of another. And same thing with the practicality. So if we can establish a framework that holistically addresses the combinations of different methods of symmetric key management, that could take us a lot further down the path of being able to effectively kind of unify not just the way that we design the systems in the first place, but enable us to cross-reference them across industries to be able to truly choose the best combined solutions for the different use cases that we have today. And that's all I've got. I'll take any questions. Thank you very much.
Okay, so that concludes our talks for this afternoon. Given the fact that we just have we're so coffee break next, given the fact that we have such a small group, I just wanted to ask, 4 o'clock, we've scheduled a sort of panel discussion, and I'm wondering what folks think. We could maybe just turn that into a roundtable with the group here, or we could just give you back an hour of your afternoon. So thoughts? Okay, roundtable, hands? Spending an extra hour in Santa Barbara? Okay, it's like 2 to 1. All right. Thank you, everybody. Thank you for attending. So we'll wrap up here. Appreciate the audience, the speakers, help from, the crypto organizing folks as well. And I hope everybody has a wonderful week. Thank you.